architect for the project. Freeman French Freeman is in Burlington. BR+A has an office in Boston, among other places. So I'm going to turn it over to Allan, and feel free to ask questions. We want to make this as interactive as we can. You'll get more out of it if you ask questions, because they can give you a little bit more than just what's on the slides if you're interested. So, and when you have questions, I'm going to go around so everybody can hear them, those questions.
That'd be great. Thanks, John. So thanks for giving us the opportunity to talk about the building directly behind you. The project started probably about 3 years ago, and it takes approximately 5 years from start to finish. BR+A is a consulting engineering company based in Boston. We have offices in Boston, New York, Philadelphia, DC, Miami, Chicago, and St. Louis. As a consulting engineer, we design, these things might flash and go to the football Patriot screen, but we design the mechanical, electrical, plumbing, fire protection, low voltage, basically everything inside the building that you see, fire alarm systems. We design that working with Freeman French Freeman, the architects. As a consultant engineer, there are multiple trades. Like I said, the mechanical side, which is HVAC, incorporates heating, ventilation, and air conditioning. We'll talk a little bit about that. We also design plumbing systems, which is all the sanitary systems and all the process systems in the building. We also design the electrical systems from where the power comes in from the utility company all the way through the building, including the lighting systems. We also have a sustainable design group that analyzes the energy for the building. As John mentioned, we try to design it in the most efficient manner. There are current codes that we have to comply with, but we try to make it much better than code. Also have an energy modeling group as part of our sustainable design group, and that informs the decisions on how we design the building. So everyone's here as a beginning entry-level engineering student, so you're all going to pick a course you're going to go down. We actually cover a lot of those. As a consultant engineer, generally you get out of school and you start working on a project, and you work with we set it up as studios. You have you work in a team organization. We try to hire people who are smart, articulate, and can work in a team environment, because projects take a lot of time to develop, and sometimes there's a lot of long nights. Coming out of school, the average wage is about $60,000 a year for a mechanical engineer. So that kind of sets some parameters for you. This is the agenda we're going to go through. We put it so that you can ask questions as we go through it. We do not design the structural systems. I think those are going to be talked about on Thursday. So, it's wide open for questions, and we welcome those in the chat.
All right. Yeah, I'll just back up a slide here. So I'm Alex Halpen from Freeman French Freeman Architects here in Burlington. And as Allan was saying, it really takes a whole team of engineers and architects to make a project like this come off. It's really like an orchestra or a concert to bring all this together to happen. And it was about 1.5 years in design. And the number of engineers involved go on and on, from your initial air quality design, your geotechnical engineers. Those are the folks who look at what the ground is like to support this building, and every site is different, what's under the ground. Your structural engineers build the bones to the building. Allan just went through all the systems that keep the building hot and cold and climate controlled and safe, fire protection. You have your tel data and your lighting, in a specialized building like STEM with over 150 fume hoods. You've got to make sure that it's safe from an exhaust standpoint. And when you're exhausting that air, I mentioned the air quality environmental engineers. They're looking at how that exhaust is going into the atmosphere and dispersed so that it's safe, and the velocity. Bryan's looking at the velocity of that air going out. We also have acoustic engineers, so they're looking at the specifics of a given room. How are the acoustics while we're talking in a lecture, to how are the acoustics when you're working next to a fume hood, to how are the acoustics in the neighborhood. So actually on this project we had a Centec come up and they took baseline sound measurements around the campus for what Cook sounds like, and we all worked together to design our new systems to be more quiet than the fans on Cook that you hear today. So there's that baseline out there, and we've got targets to beat that. But being the architect, and one of the other engineers is another architect. So we do some of the largest projects in the state.
You have to set the timing on this thing.
Okay, yeah. Haven't done any stadiums yet.
Yes.
We do some of the largest projects in the state, and we, on this project, a very specialized laboratory building, we also bring in a specialized architect, and that's Elmswag out of Boston on this project, to design these labs very specific for a STEM building. And on the STEM building itself, it's about 194,000 square feet. It's also linked over to the Vody building, where many of your classes are today. It's designed in an interesting shape in that it's kind of two wings, and that was driven by the phasing of the project. So projects start out with a bunch of steps, and I'll get back to the phasing in a minute, but the initial part of design is figuring out the program of the building. And so the program is what are the activities that are going to happen in and around the building. And that happens early on with narratives and diagrams indicating how much space, indicating what activities need to happen adjacent to one another, and the types of systems that might be brought in. So engineering groups like BR+A will be involved to say, hey, you want to have these types of labs. They'll write a narrative on the types of systems. And so we develop a program for the building, start to define how big it's going to be in a narrative format, and then we go on to actually putting a shape and a design to the building. And so this image of a schedule is just one snapshot over the overall 5 to 6 year project plan, and this is in so this design development phase is kind of in the middle of design, and you're seeing about a little over a year from once you kind of got the shape of the building to developing the construction documents to build it, and then it's a 3.5 year construction project from there. So back to the shape of the building is once we figured out all these activities in the 194,000 square feet of space and activities that have to take place, we looked at how could we reuse the Cook building that's there today. It's an enormous 112,000 square feet building. Its structure is fine. It's been working well for 50 years. Can we reuse that? So we took a look at it structurally. It was pretty sound. Took a look at it mechanically for the new systems that had to go in there. Well, the floor heights were pretty narrow because we've got lots of big ducts running through this building. So that was a bit of a challenge. And then we looked at it with the program. How can we fit all these spaces in that building? Well, some of the spaces were too short. Some weren't long enough. So we started to have to move walls. We had to move structural columns. So the more we looked at that, and we would put cost estimates to how to renovate that, we exceeded a threshold in renovations of an old building, which then the codes say, once you exceed that threshold, you have to now make that old building meet current codes. So it meant we'd have to add all kinds of new structural steel to stabilize that building to meet the seismic requirements for today. And it also meant that the mechanical engineers had to do all kinds of fancy footwork to get the ducts to fit in these tight spaces. So all said and done, it was for the same price, you can build exactly the building you want, exactly where you want it, and make a modern building that really functions well. Back to the two wings, we would displace all of the chemistry and physics departments that are functioning right now for 3 years if we were to reuse that building. So one of the nice things about building new is we were able to construct this lab wing now so that in the fall of 2017, over next summer, all the occupants of Cook can move out of Cook and occupy the lab. Then Cook will come down, and then we'll build the classroom wing. And so these schedules are a big part of the process. This is just a more detailed schedule, so along the way, there are literally probably 100 users that are participating in the design of this space. So you can imagine designing your own home where you're dealing with 2 to 4 people to figure out where your different spaces are. We've got, the chemistry department, the math department, the engineering department, mathematics, and they'll build user groups to inform what needs to be in each space, the temperature, the humidity, the acoustics, all of that, and we all work together to make that happen in each space. So this is just one of our monthly schedules throughout design where we schedule these meetings to make sure we're all communicating. So communication is huge, how you communicate with one another, make sure everyone's hearing the same thing. And back in the day, like when this building was built, there might have been one architect. You look around, you see there's no heating ducts in here. There's no air movement in here. It was really a top-down process with the architect a long time ago. And today it's much more horizontal. And we bring a lot of specialists together to make these modern buildings really work very well. So this is the original site plan that we looked at in the beginning. You can see Cook building here and Angel, and we knew this was the site that UVM wanted to put the building in. It was the steps I just talked about to get where we are today. And in that communication process with modern design tools, we use sophisticated CAD programs and 3D modeling, building information management systems in order to put this all together. And Allan and Bryan will get into that in more depth. We as architects look at it and how it creates space throughout the campus. So if we're going to take this quad and fill it up, we don't just want a series of leftover spaces. We want to create some outdoor space where people can communicate and have opportunities to live in. So that model, the first one was more about the exterior skins of the building. These models are fully dynamic. You can get in and start to look to see how the systems interact. You can cut sections through them and get into the details, which is very important because you can see, well, we've got a structural beam going through a piece of ductwork. We've got a light fixture that's in a window, and those things have become evident in the model.
So as part of our design programs, there's a company out there called Autodesk. They seem to own everything in the world these days. And we use the Revit program, and it changes every year. We have to buy software every year to upgrade it. So currently we're using Revit 2016. And most of these images, and you'll see a model in a couple of minutes here, were all generated by that Revit program.
Revit has been, just in the last 10 years, has made huge leaps and bounds in terms of communication. So we designed this building with a single model and a single file. So we're working with consultants from Boston and Toronto, and it's seamless. So you can upload your changes. If 2 people are changing one thing at the same time, it lets you know and flags that. And it really would take probably another year or so if you could even do it without. And you can do it without, but the number of conflicts and clashes between systems goes through the roof. So we've been able to really accelerate and coordinate the systems well.
So I'm not sure, will they take SolidWorks or something like that? SolidWorks, yeah. So that's a very similar program, a 3-dimensional design program. It just so happens in the building industry, Autodesk has the strongest following in the United States, and that's primarily, and not only from a design, so we generate a model that we turn over to the contractors. in the case of the STEM building, it's PC Construction is in charge of it. They're the construction managers. So we, as a design team, the architect engineers, develop this whole model, and then we turn it over to the contractors to build. And then they develop their own model in similar programs. It's still in the Autodesk world, but they use Navisworks and some other programs. So it's fairly involved in the overall design process for the building.
So I'll turn it back over to Allan, but just wanted to show you our cover sheet. That set of documents to build this building is 250 sheets of drawings that are about half the size of this table, with tons of detail. And it just goes back to the whole thing about communication.
Thanks. So is this where we jump to the model? So here's a picture of the BIM model stripped down. So how do we get to this? We get the exit.
So we'll just go. The opening picture is just the structure and what we do, what I do as an HVAC engineer and a project manager that coordinates the electrical and the plumbing as well. Is we start with this structure and we start with an architectural floor plan where the architect always likes to put the ceilings like way too high, so we can't fit any of our ducts and stuff. So then we get into the model. We got to coordinate that stuff so that it's not all stacked on top of each other, but fitting nice and smooth, so that those ceilings can be as high and the spaces can be as open and pretty as possible. So this is just an image. I'm going to actually go to a model walkthrough of our Revit model, which has multiple trades. We're going to kind of overlay each other. So we'll start with just the kind of the skeleton. You peel it back, and you see just these are just the electrical systems
In yellow.
in yellow.
So that's conduits and electrical panels.
So yeah, but electrical systems are don't take up a whole lot of space. It's just conduits. Then you overlay the plumbing, and you're looking at a whole lot more pipes. You see, Alex was talking about the two phases. This building here is the lab building. The one in the back is the class building. You'll see a lot more plumbing in the lab building. All the lab gases and water and pure water and stuff like that takes up a lot more.
The other thing with the plumbing systems is that they have pitch to them. So plumbing systems have to drain. So and it has to have a straight shot. So they take a lot more coordination effort when you're designing the building.
So there's all the plumbing system overlay, and then it gets a little more complicated. You see the red is the fire protection. Again, just kind of one pump, one pipe system.
With sprinklers.
And then you put the HVAC system on top of all that, and now you're looking at a giant mess of equipment and piping and wiring that all needs to be coordinated.
Yeah. So these are the air handling equipment that we're talking about. Supply air units with large ducts that come down through the building. Exhaust stacks. So when you go outside, you can look at the building. This is in the mechanical penthouse up here. And it took a lot of effort to design the penthouse to fit within the structure, and then the shafts that come down through the building. You have to. We'll talk a little bit about designing these individual components.
So that was just the supply system that was overlaid first, and put the exhaust on top of that, and you see the major shafts that Alan's talking about that go down and feed each floor from each north and south. So now walking through the model here, and you can do this using a program called Navisworks. It takes all our models, combines them into one. You can shade them to look at as solid instead of just wireframe. So it's a real skill to be able to use that product. It's a very good asset to have, so that you can go through this and see how things actually fit. We used to just draw things in 2D CAD and leave it up to the contractors to make it fit. But now with the power of the software, it puts a lot more of that on our plate to make sure things work when they get out into the site. And avoid costly coordination issues if we don't make it work up front. So just flying over the top of the mechanical room here, like Al said, we've got our main air handling units with the big stacks off the top of it. So that's all your fume exhaust, your nasty stuff that you really want to get a high velocity out of the top of the building to keep it away from other air intakes and other potential contamination.
So as an example, the organic teaching labs would go in, or the organic labs, the exhaust would go into the system and then be pushed up into the atmosphere. Alex mentioned it earlier, there's a consultant that actually looks at the airflow, the velocity of the wind in the area and the topography to figure out how tall those need to be. So it's another branch of engineering that's out there.
Yeah, they actually will build a model of the campus. They didn't in this particular case, but they will to get real detailed actual wind analysis of how that affects what comes out of the stacks. They also can use computer fluid dynamics to be a little bit easier method of accomplishing that. So again, all the exhaust comes up through those stacks that you'll see out on the top of the building, anything that's potentially harmful. So that's the crux of the mechanical room. The penthouse is the air handling systems. You come down into the 6th floor. This is kind of a typical lab floor. You see the blue duct through the middle of the floor. That does your supply air to all the labs. You can see diffusers coming down that. We have the architecture stripped away here, so you can't see actually what's going on. We'll cover some pictures later what the stuff actually looks like. But you've got the cable tray that does all your tel data. Again, the red pipes are the fire protection sprinklers. The gray pipes are all the HVAC, chilled water, hot water piping that keeps your environment cool. And the gray ducts are the exhaust that connects to all the fume hoods, gets the contaminants out. So you can see a lot of stuff above that ceiling and some really big ducts that you could easily crawl through, and the ones in the penthouse you can walk through them, they're so big. So just going through the floor, again looking through where these would be walls that we're looking at. We've got multiple vertical pipe risers and conduit risers that all need to be coordinated from what the voltage requirements are and to feed all of the lab equipment to the pipe size for all the particular cooling and heating needs on that floor. So again, this Navis simulation is a good tool to look at how this stuff actually works. And we'll run a clash detection. You might even see a couple in this model to draw our attention to where some of the big hits are, where things aren't going to fit through the corridors of the building. And if it doesn't work, then we got to move the stuff out into the labs. So that's kind of the process we go about as mechanical, electrical, plumbing engineers. We're looking at everything, how it fits together. So coming back out the building, look at the main duct shafts, supplying exhaust. Down into the basement, you've got the main fire protection, fire pump room right there on the right. The main water comes into that side. And you'll see all the yellow, orange equipment right there is all the plumbing equipment. In a lab building, you've got RO, reverse osmosis water, deionized water. You've got compressed air, vacuum, and other gases that need to be distributed through the building. And this is the heart of all those systems. And then beyond that, there's a multitude of mechanical heating and cooling pumps and heat exchangers that all need to be sized based on specific loads. Because, this day and age, you don't want to oversize things because there are energy codes, and we want to make sure things operate in their sweet spot to reduce the energy use. So you can see that's kind of a snapshot of what we produce as far as documents. And then we'll get back to the slideshow right now. Again, just going through the structure, electrical, plumbing, fire protection, and the HVAC systems. And all that stuff really, like I was saying, needs to be sustainable. So I'll turn it over to Al to kind of cover a few of the major topics that both architecturally and mechanically we need to address.
Okay, before we go ahead, any questions from anybody? Anybody? Yes, it's Revit, Revit 2016. And the name of the company is Autodesk. AutoCAD was the preliminary. We used to design buildings in 2 dimensions. That's kind of ancient history now, but about 10 years ago, it converted over to 3-dimensional design. And so the program that started off, there were 2 or 3 programs that were going neck and neck. Autodesk basically bought all of them and merged them into one. So there's a big conglomerate out there right now.
I don't see how that's going to really make a big change in the industry either. So if you can push your instructors to make a push for Autodesk, that's what we would recommend.
Yeah. So everybody. So and the contractors also have separate software packages in the building. The reason why we mention HVAC versus electrical, they're all broken up into sub-trades. When you do a construction project, there's generally a construction manager. In this case, it's PC Construction, used to be called Pizzagalley. And they hire subcontractors to actually do the work. Are they self-performing any work here? Yeah. So generally, they only hire people. They just manage people. And that's one of the nice things about seeing a project from start to finish is that you get to see all the different trades put together and how it all works together. So we produce design documents. They send it out on the street and it's bid to subcontractors. There's a concrete subcontractor. There's a structural steel subcontractor. There's an HVAC subcontractor, and that's what we're talking about here. There's an electrical subcontractor. I don't know how many sub-trades there are. There's probably 20. Yeah. Masonry, there's all the brick, the windows, 30 sub-trades on a construction project. So you can imagine that, these things are complex projects with a lot of moving parts and a lot of people involved from start to finish to give the owner a very distinct building. It's not generic. It's not, you can look at a McDonald's and they've reproduced all over the country and they're very similar. We're designing a unique product here. From a sustainable design standpoint, we took into account the building orientation, how it faced east, west, north, south, and the wall-window ratio. Why is that important? Windows have less insulating capacity or value than a wall. And the walls can have more thermal insulation in them so that you have less energy use. We looked at the insulation values in the building. That's what Alex does, and he'll talk about that a little bit here. The windows, you may not consider this, but windows transmit light into the building, but they also transmit heat into the building. Because, the sun bakes in the windows, heats up, especially a room like this. This has a very high thermal mass, meaning that it has a lot of brick. So you can imagine that the sun beaming in through the window, hitting that surface, it's going to heat it up, and then the heat gets radiated back out again. So we look at that. So we look at the solar heat gain coefficient of the windows and the shading coefficient. Shading coefficient is how much of a tint the window might have. Sometimes they're clear, sometimes they're green, sometimes they're gray. We have energy recovery systems. So all that we were mentioning these exhaust stacks and all the air that gets exhausted from the building because we don't want the rooms to be smelly. The air comes in from the outside, 100% outside air flows through an air handling unit, gets distributed to this room. Like we open up windows in this room because this is ancient history here, right? In the new building, the air comes through an air handling piece of equipment and gets distributed by ductwork. And then that air gets exhausted from the building. So what do we do to make sure that the building is more efficient? We recover the energy that's being exhausted. There are a couple different ways of doing that. A heat wheel is one way, so the air passes through the wheel on one side, it rotates to the other side and preheats the air coming in. Or another way to do it is in a glycol system, a water system, a water-based system where the energy is transferred by a pump system. I'm not sure if you've had a chance to see it, but there's a central energy plant next door to this building. It has boilers in it and it has chillers in it. And there's a distribution network around campus underground that distributes the steam and chill water to the campus to keep everything all the right temperature. Okay. Yeah, we'll get there. So we look at how to make sure that amount of energy gets reduced for the building. There's also outside air that I mentioned before. So in order to reduce the amount of outside air coming into the building, we look at the things like fume hoods and other things that make the exhaust requirement higher and try to reduce those. And we do this all with a life cycle cost analysis. So here's a picture of the building. You can see how the building is oriented. There are the wall window ratio, as I mentioned, that these are the windows. So that percentage was looked at. You want to have good visibility inside. You want good lighting, natural lighting inside the building. So it's always a aesthetic decision that happens with the architect.
You want natural light to reduce the amount of electrical light that we're using in any space.
Yeah, during the daytime. So here's a pic. We also worked on what used to be Fletcher Allen, that's UVM Medical Center. They designed a new bed tower right up the street here. So we also worked on that. And this is a picture of the preliminary renderings of what that was going to look like. We have a chart up here where we analyzed how much glass there is. You can't see it. It's like an eye chart from way back there. But we looked at So this chart has, you can see it if you, maybe people in the front row, but this says U value, and it has different U values associated. Solar heat gain coefficient, overhang ratio, and this is the orientation north-south. And what we tried to do is analyze what the best orientation for the building is, how much wall window, how much shading, like these are solar shading things. So this analyzed and it picked this one particular thing as the best design for that building. Now, I'm not sure if exactly they used that, but at least it was a tool that they utilized to understand how they could make this building better.
So Allan was talking about the thermal efficiency of the envelope of the building. We always start a project, and I've been doing this for about 20 years now, and it changes probably every 5 years how we're insulating the outside of the building. In this building, there's no insulation other than the masonry brick itself, which is very poor insulation. On this job, surprised us again. So through BR+A, they did an extensive energy model, understanding all the systems in here that are blowing out the exhaust air from the fume hoods. As architects, we're like, we always try to push the amount of insulation in the building. We want to maximize it. Thought that'd be great. So we looked at doubling the amount of insulation on this building. And Bryan called up and said, all right, I just plugged in the double digits here for insulation, and it's not doing a thing. So we were ready to follow what we've been doing on a lot of projects, but it did not apply at all to a laboratory building because it just exhausts all this outdoor air. And the energy model was enlightening because it said you need to put your investment into an energy recovery system like Allan was talking about that recaptures that exhaust air and that energy and heat in that air and puts it back into the building. So there's a wall section. You can see the two lines on there.
Does anybody know what a section means? It's a cross section of the outside wall. So if you looked at this wall and cut a line right down through the middle of it, that's what it's looking at. So as an example, you have this is insulation. It's bad insulation here, and then that I believe is rigid insulation, and there is a stud like here that holds the wall together, and there's the floors right here. So this is what architects use to do and how to show the contractors how to actually construct the building.
Yeah, that's a great point, Allan. And heat and moisture are constantly moving in and out of a building. We try to control that these days. So from a heat standpoint, we bring our insulation under the floor, up the wall, around the wall, and over the roof. So one thing we do is we put our pen on paper and we trace that line all the way around the outline of our building to make sure there are no breaks, because it's actually quite easy to have a break. If you've got pipes going through the floor or walls that go outside the building, we do that. So that's the thermal envelope, and then this dashed line comes up through, and that's usually some type of rubberized membrane which stops or greatly impedes the transfer of moisture in and out of the building. And we keep that in Vermont on the warm side of the insulation, and that stops lots of mold issues. This is the wall section we did at the Waterbury State Office project, and this is a wall section for STEM, and you can see the insulation has shrunk quite a bit. And these are all the components that go into any standard wall.
So HVAC, heating, ventilation, and air conditioning. I didn't know what it meant when I went to college. I went to UMass Amherst. I took engineering, mechanical engineering, and I took one course on HVAC, and I really liked it. And then I took a course in solar engineering, and that showed you how to design a building based upon where the sun is located, and a couple others, one in wind energy. And I had no idea what I was going to do when I got out of college. So I happened to be with a friend of mine, and we were like, yeah, let's throw our resume into this consulting engineering company. That was back in 1981, and I've been working as an engineer ever since. So, believe it or not, you might end up in exactly where you intend to be. So, heating, ventilation, air conditioning. Heating is heat loss. The flow of energy through the building. So this space is 70 degrees. The outside is 20 below zero. Heat flows through the wall. Energy flows through the wall, and the more insulation you have, the less that it impedes the flow through the wall. Ventilation is the amount of air you supply into the building. The newer buildings have more airflow because when you have airflow in the building, less people are falling asleep. It's better indoor air quality, and you also control contaminants. Air conditioning is the tempering of the air in the building. So generally, most buildings these days are air conditioned. They're very, very rare that we don't air condition buildings, and that's to control the temperature and relative humidity within the building. Heat loss, if you take mechanical or mechanical and maybe chemical engineering, you'll learn this equation quite a bit. UA delta T. U is the U value of the thermal of the wall assembly or the assembly that it's going through. A is the area of the building, and delta T is the temperature differential. As I mentioned, the design temperature for Burlington, Vermont is 20 below zero. 20. So we figure out what, and I'm not sure if you're taking it in SI units or BTUs, but we figure in the United States, everybody uses BTUs as opposed to kilowatts. So we use the BTUs per hour is the flow rate through the wall. It's the U value times the area times the temperature differential. We used to do this all by hand, but now it's all computerized. You can actually use the Revit model as the baseline, so you can get all the information instead of actually physically going in and measuring all the different components. You can use the computer to do that for you, and it generates what the load profile is or the load analysis. So each individual space in the building gets a value from that. And then from that, you can figure out what the annual operating cost for the building might be based upon the energy costs. Ventilation, this is, hopefully you'll get the chance to take a course in this, but this is a psychrometric chart. The x-axis is the dry bulb temperature, which is the temperature that you read on your thermometer. This axis, it's not exactly the y-axis, but this axis is the dew point temperature, and this is actually the dew point of air. So as you cool air down and it hits the dew point line, that's when it condenses out. It's what you see on the glass in the summertime. So you have a cold glass with ice in it, and the air hits it. It's all based upon the psychrometric chart. This is the properties of air and water. So we use that to understand what the cooling requirements are for the building. Ventilation. This is an air handling unit that's in STEM. If you walk out the door, walk up the stairs because you can't take the elevator, and walk up to the penthouse, this is the air handling unit. And you can see that this is a supply and exhaust system. The exhaust is sitting up on top. It's a big piece of equipment. It's approximately 12 feet wide by 45 feet long by 12 feet tall, and it costs a lot of money. You want to go through the components?
Yes.
Sure. So this is a section of the air handling units that are right across the street. You can see them if that wall wasn't there. But illustrating all of the different components inside the unit that we, as an HVAC engineer, I need to evaluate how many and what size fans are the optimal fans to move the air from point A in the penthouse down to the furthest point in the basement, which consists of a static pressure loss calculation from every fitting through the ductwork, and then from there you're blowing air through the coil. Coil's another static pressure loss. You need a fan to be sized to overcome the pressure drop from blowing the air through a coil. This coil being so in this particular unit we have 3 separate coils. There's actually, so I'm going to go from where the air comes in the unit on the supply side. So supply comes in this side. We hit first, a set of filters. Filters will keep your air clean, and there's a code requirements for that. But the first big set of coils that we hit is the heat recovery coil, which I think is this guy. So the heat recovery coil, that's the one where you take, it actually has a paired set of coils up here. So this is where you pump glycol from the hot exhaust air. Exhaust air comes from the building, goes through the exhaust unit, up the stack, but it goes at 75 degrees. So when it's minus 20 outside, like it gets to be up here, you take 75-degree air and you pump that, use that to heat up a loop of glycol. Glycol is just water with the antifreeze in it, pretty much, so it doesn't freeze. And then the minus 20 air comes in and hits that. It's actually this way. And it heats that air from minus 20 up to 10 degrees. So that's free energy that you're just using the air from your building to heat up. And it saves the amount of work that your actual heating coil has to do. Actually, there is only 2 coils in this one. So external to this, there's a heat exchanger where if you can only heat the air up to 20 degrees with the minus 20 outside air, the heat exchanger will do the rest and get it up to a comfortable discharge air temperature. And oftentimes, even when it's cool out, we need to use the cooling coil to dehumidify the air. So Allan talked about the condensation that builds up on the glass. If there's condensation building up on your glass in this room, that's not a good situation because that's uncomfortable. You're too close to the dew point line. So oftentimes we need to run the cooling coil in those shoulder seasons just to get it more comfortable inside the space. So that's the main components of this system. To go along with each of those coils, there's a pump that needs to be sized also for a different type of water pressure drop through the entire system. So those are the components we spend a lot of our time focusing on getting the correct sizing for, so that the contractors can buy them and put them into the building, and it works. Everybody's comfortable. Specifically inside that unit, that is what the fan array looks like. So this particular unit had, I think, 6 fans stacked on top of each other and side by side. And this is a pretty standard technology in buildings, fan array or fan wall technology, it's sometimes called. It reduces the one big fan to multiple little fans. They're easier to maintain. And if one fan goes down, you still have redundancy to run your system, especially in a lab building, where that's a serious concern. If your air system goes down, your lab gets, your fume hoods cannot operate or become an unsafe condition if the fans go down. So that's why there's multiple stacks on that building, which are redundant fans, so the fume hoods always remain safe. So these pictures just illustrate all the ducts that go down and the pipes that cross up. And these are pictures from right across the street. In the model walkthrough I was showing you before, this is the main supply duct down the corridor. That model doesn't even show all the conduits that end up getting thrown up there after the fact. We don't actually model every half-inch conduit, but that's what's required to operate, to run the lighting in all the spaces. And if we don't draw it, we need to account for that space to fit in above the ceiling. So that's some of the stuff we do on the supply side. The exhaust air side, this is not on that particular building, but it is an example of a type of technology that's used to disperse the exhaust air, the contaminated air up from laboratories up as high as you can. So an effective plume height is what we're looking to achieve, where it's safe and away from other occupants or air intakes. Allan was actually talking about the company, we use RWDI, they do the the analysis. And this is just a chart of the prevailing southerly wind here in Burlington that we used to figure out where this exhaust was going to go after we throw it out the building. That's the exhaust system. We talked a little bit about the energy recovery system now, but this is the crux of the energy that we have to recover. It comes out of those stacks, and wherever we can push it back into the supply side is what we got to do. It's code requirements now, not just good practice. So, refrigeration cooling. Did you want to talk about the central plant stuff?
Sure. Yeah, I'll jump on that one. So you probably recognize this. That's the Cook Building. This is a cooling tower enclosure that's out there. You may not know that it was that, but they have they had four cooling towers. They're adding to that. There's an addition going on the end of this building right now to add more chillers to the building. So the refrigeration plant is housed in this building currently, and they're making it larger because of all the construction that's going on campus. There's chillers that generate chilled water. Chilled water generally has to be around 42 to 44 degrees to be able to dehumidify air. They're located in that plant, and as I said, the cooling towers reject the heat from that. So you'll learn the refrigeration cycle and thermodynamics if you take mechanical engineering. So this is a picture of the of that cycle. You have up here a chiller. That's what it looks like. It's a huge piece of metal. It weighs probably 20,000 pounds. It has an evaporator bundle and a condenser bundle. The evaporator makes the chilled water side of things, cold water, and then the condenser bundle rejects the heat, the cooling, and it rejects it through the cooling tower. So you'll learn theory behind how those actually get designed. We are application engineers. We take products and apply them, and as part of our practice, you have to get to know manufacturers, you have to get to know products, you have to get to know a lot of different things and be experts at it, because everyone expects you to be an expert. Another thing that you're going to be taking in courses in mechanical is fluid mechanics. All the pipes in the building, whether it's chilled water, hot water, or any of the plumbing pipes, are all subject to friction losses in the piping. So you have to size the piping based upon the flow rates. You've got to calculate what the flow rates are required in order to heat and cool the building, and then you have to size the piping. From that, you also have to figure out the size of the pump, how big the motor has to be. This is an example of a pump curve right here. There's a picture of a pump. You can see the water comes in this end, it goes out that end. It's called an end suction pump. This is a pump where, if you looked at it at 1,000 gallons per minute at 450 feet ahead, that's the optimal point to select the pump. It's the highest efficiency. Generally, we design these systems. This is a manufacturer. That's Bell & Gossett pump. It's a red pump. Everybody knows a red pump is Bell & Gossett. So other manufacturers out there have different color pumps. But they all have a pump curve with a total dynamic head that's on the y-axis, the gallons per minute on the x-axis. These are the sizes of the impeller that actually goes inside that pump. And, again, it's something that you have to work your way through in the design of the building. Electrically, I'll touch on this briefly. I'm not an electrical engineer, but I get to see it a lot and I understand the systems. The electrical power comes from the utility company. So it comes into the building and it goes through a transformer. Then the transformer runs into a switchboard, and then from the switchboard it runs through the various distribution devices to get to where it needs to be utilized. So as an example, you're going to be splitting up, most of the building gets split up into three different components. One is the building equipment branch, which includes all the HVAC loads. There's also the lighting branch, which is 277 volt generally, although that's changing with the LED lighting. And then there's the plugs that go into the walls all around the building or onto the bench tops. So electrically, you have to figure out what the loads are and kind of back it all the way down, similar to the HVAC side. You have to design it all the way through the It also has standby power systems. This is a picture of a generator that could go into the building. Caterpillar is one of the major manufacturers out there. It's an engine and a generator. It does have a radiator just like a car. And it has the generator part of it, so it generates electricity that gets fed through a paralleling gear generally into the electrical system for the building. It provides standby power, which basically allows you to run things when the power goes off, and life safety systems, which is a code requirement that you have the fire alarm systems on it, the egress lighting systems on it, and some of the other components.
On the STEM building, this is a really important part because you've got researchers that are doing experiments that take years to complete, and if they lose power for 10 seconds, they can destroy their experiment. So these guys designed a thing called a transfer switch in a different way, but they'll transfer from a power outage to emergency power very quickly for this process. Whereas if you have a hunting camp or something, it doesn't matter if you're down for half an hour, pull the cord and start the generator.
Right. And as Alex mentioned, some of the things that we look out for are critical laboratory equipment. In a lot of cases, there are minus 80 freezers in the building that the research people utilize to put samples in. And if they lose power and they lose the ability to keep that at minus 80, they lose those samples. In some cases, they could be almost a lifetime of experiments and work going on in those. And then, as I mentioned earlier, that from a building standpoint, lighting is a very important component. Not only natural light, but artificial light. Artificial light, generally we're using LED fixtures. They're substantially more efficient than fluorescent fixtures or compact fluorescent. So we're trying to make sure that you know this term, LPD, or lighting power density. We used to design for 1.5 watts a square foot. We're down to 0.5 to 0.75. So the amount of energy consumed in lighting in the building has dropped more than half. But we still have to maintain a foot candle level so that when you're writing on a desktop, you can actually see what you're writing on. So all those components go into the electrical design side of the project. So that's what we have put together for a presentation. Hopefully I kept most of you awake. So I'm opening it up for questions now for anybody. So I think the next thing you're going to have to do is take a tour of the building.
I have a question, though. Maybe I'll
Sure,
start.
John.
Do you have any filters on the exhaust here?
Generally not. I mean, we put filters. So if we go back to the components on the section of the units, the air comes from the building, so it should be clean. Generally, the air from the outside is dirty, although up here in Vermont, the air is nice and clean. Generally, we put, because of the air, so this is the air coming from the building. We'll put filters in to protect the coils. The coils are here, so we don't want things like Kim wipes or any other things that generate dust and dirt in the building to get and foul up the coils, because we try to keep them as clean as possible. So yeah, we do have on the energy recovery exhaust systems, we do have filtration. We don't on most other exhaust systems.
I'll add to that a little bit. One of the things that we did evaluate in this project, particularly that was unique, is there's a lot of fume hoods, and there are particular teaching fume hood labs where the chemical usage might not be so random and a little bit more known of what's going through those teaching hoods. We looked at doing filtered fume hoods, which is non-ducted, so it actually recirculates, puts the exhaust air from the chemical tabletop work area through a filter, a HEPA filter. Filters need to be changed every 1 to 2 years, but it means you then don't have to exhaust that entire room, which is a huge air volume, which is every CFM is the unit that we use to measure air volume. Every CFM that goes out of the building is another CFM that you got to bring into the building and heat and cool. So, we were talking life cycle cost analysis. That was one of the big ones. These filtered fumes did not end up making it into the building because there just weren't enough of them to make it economically viable to go with that whole system. And we found that putting our money into the high efficiency energy recovery system was more beneficial over the lifetime of the building. So, just stressing, I think one of the things that have become and will continue to be more important in our industry is really evaluating how much energy something will save by implementing it into your design versus how much it costs versus how much energy it will save over the long term of the building. So life cycle energy is something we do in our energy models for pretty much every building nowadays.
Okay.
Do you take into account maintenance on the building, and do you plan for that over a certain period of time? If so, for how long?
So you could, the general, when we design the systems, we design with maintenance in mind. So as an example, if you looked at how the equipment's laid out, there are, we allow for space. We put in ladders. The systems that we select are more durable, so they have, generally the universities are hard pressed to keep things in good working order. They're very thin on staff. They don't have a lot of extra funds laying around. That's why we're trying to save on the energy side, because that's part of the operational budget. So yes, we do provide ways to maintain it, but we're not involved in the maintenance side. Basically, we design it and we turn it over to the operations side, and then they take care of it. But as an example, the motors have this L10 200,000. So that means that it's good for 200,000 hours. If you take 200,000 hours divided by 8760, you can understand that it's good for a long time. So we try to pick all the components in the equipment to make sure that they have a longer lifespan, but you still have to grease bearings, you still have to change filters, you still have to do a lot of different things in the equipment.
Well, we guys work really closely with the university and their standards. So they might have a particular type of valve or light fixture that they use in 50% of buildings. So we'll make sure to use that same type. So replace the bulb.
Yeah, the university maintains a fairly strict standard for equipment and systems. So, yes. He's the aesthetic guy.
Absolutely. So we're saying this building's right behind the most historic buildings on the whole campus. And so height was a big concern. The shape of the roof. We started out with a building that had a flat roof, very modern glass building. But these are concepts. You got to. One thing you learn early on is that you don't get attached to your ideas. You might have a great idea, but you throw it out there and then you troubleshoot it and you look at it from different angles.
And usually the president has a pretty good opinion.
Yeah, the administration has an opinion as well.
Right.
But aesthetics were a big deal, and we didn't. University was focused on that, so we used real stone. There was an option for cast stone, which is basically a really pretty concrete fake stone. We stuck with limestone. We stuck with real brick. Stuck with real metal panels. We stuck with real slate on the roof itself, Vermont slate. So that was very important to be in the background here. We also align it with walkways, accessible walkways, alignments with the green. Aesthetics are a big deal, and aesthetics are a big deal for engineering because
we have to hide everything. People don't want to see it. They don't want to hear it. They want to be comfortable. So that's what we have to do as an engineering company.
Absolutely. Every wall in the building is.
And you got to be perfect.
It's maintained with pipes and conduits.
So yes.
Can you clarify the 8760? I'm not sure if everybody knows, but what that
Okay,
number is.
8760. Anybody have an idea what that means? Anybody? Yes. Yeah, exactly. 24/7, 365. 8760 hours per year. Anybody know how many work hours there are in a year? If you work 40 hours a week? I get all those in my head. I get a lot of numbers in my head all the time. So, you're welcome to stay and ask us questions. We're always looking for engineers, graduate engineers. I had